Hello all, welcome to the Basics.Academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. This is Smart Contract Security Lab Sessions. What we are going to do? We are going to reproduce 4 real hacks, then fix them. What are those 4 hacks? First is the DAO, second, run-in, third, wormhole, and fourth, the poly network hack. Each will be run as a Hardhat lab. Important thing to note over here is everything runs on a local test blockchain, no real funds, no live systems. This is a safe sandbox to learn in. What we will do today? We will learn to see a bug the way an auditor and an auditor does. First, we will reproduce the hack. Secondly, we will understand the root cause. Thirdly, apply the fix, and at last, name the principle. The 4 labs at a glance. 1 incident, 1 bug class, 1 fix per lab. In case of reentrancy, the bug is external call before state update. The fix is checks effects interactions pattern. In case of access control or the run-in bridge hack, the bug was key custody plus no distinct signer check. The fix is distinct signers plus off-chain custody. In case of wormhole hack, it was signature verification. The bug was trusts a caller supplied proof. Fix, pin the verifier at deploy time. And at last, poly network hack, the privilege trap. The bug was over privileged executor. The fix is to use a whitelist target plus a selector. Every lab follows the same rhythm. Learn the loop once, it repeats for all 4. First, read the flawed contract. Second, run the attack or the exploit. The attack works. Third, fix the attack, patch the one weak spot. And last, rerun the test. Then the attack fails. Seeing the exploit succeed, then fail, is what makes the lesson stick. Let me repeat it once more. First, we will look at the flawed contract or the vulnerability. Second, we will run the exploit and see it works. How we are going to test that? We will test that using unit test cases. Thirdly, we will fix the vulnerability, and at last we will rerun the test and ensure that the hack never happens again. One-time setup which is needed for all the students to run on their system to get started with the lab sessions. First, open a terminal, create a new Hardhat project, SCS lab. Then, copy the contracts directory, reentrancy test file, package.json, and the readme file which was shared on Google Classroom. Then refer reentrancy test file, and following is your task. Each student is supposed to write unit test cases for the access control smart contracts, then the signature verification smart contracts, and at last the privilege trap smart contract. The name that you see on the screen for access control, signature verification, and privilege trap, the contracts for these hacks are also shared on the Google Classroom. All you have to do is write unit test cases. Writing unit test cases ensure that you understand the bug, you run the exploit, then you fix the bug and again rerun the exploit and find out after fixing the bug the exploit doesn't work. The whole purpose of unit test cases is to make sure that the student understands the bug end to end completely and is able to explain those bugs to anyone who asks them. Once those are completed, you are supposed to run npm install, which will bring in all the necessary dependency packages. Then compile the contracts. After compiling the contracts, you have to run the test cases and ensure that the exploit works before the fix, and after the fix, the exploit doesn't work. Notice everything is local. Hardhat spins up a throwaway blockchain in memory during each run. What you will need? You will need Node.js 18 plus and npm installed, internet for running npm install once, any code editor, but I would recommend VS Code, no wallet, no testnet, no real ETH. After completing the labs, how are we going to run those labs? You can run all 4 labs at once using npm test, or one lab at a time. If you want to run access control hacks, use the command npm run test :access. A passing vulnerable test means the exploit worked. That's the point. And after fixing the exploit, that same test case should not work. So what to expect? Each lab prints 2 results. A vulnerable test where the exploit succeeds, then a safe test where the same attack reverts. Lab 2 adds a lesson: stolen distinct keys still pass. So while doing lab 2, just have a look at stolen distinct keys. How to run each lab? It should not take more than 1 hour. However, I understand as students, you will be doing it for the first time. So if it takes more than 1 hour, that is also accepted. What you have to do is, you have to read the vulnerable contract. After reading the vulnerable contract, you have to run the exploit. The exploit is one of watching how the DAO contract is drained, then the minting or the takeover happening live. Third, you have to read the fix. Fourth, you have to run the safe test. The same attack now reverts after fixing the vulnerability. And at the 5th step, you have to name the principal. While naming the principal, you are connecting the bug to a secure coding rule. So here, you are learning while implementing. Ground rules and ethics. Security skills come with responsibility. First and foremost is local sandbox only. These exploits run on a throwaway chain. Never point them at systems you don't own. Second, you should learn to defend. We study attacks to build safer contracts. The fix matters more than the exploit. Responsible disclosure. Found a real bug? Report it privately. Don't exploit it. Unit 5 covers this. Real stakes. These bugs moved billions. Treat production code with that seriousness. An auditor breaks things to protect people. Keep that framing in all sessions. Let me repeat. An auditor breaks things to protect people. Keep that framing in all sessions. So are you all ready? Let's start with the lab 1, which is Reentrancy, the DAO. For lab 1, I will be explaining the vulnerable DAO contract, then the safe DAO contract, and thirdly, I will be explaining the entire Reentrancy unit test case file. Based on this, you are supposed to complete the unit test cases for access control, signature verification, and privilege trap. So let's get started. First, let me explain the DAO hack. We will start with the vulnerable DAO contract. Here, I have the smart contract security labs directory. This is a Hardhat project. This is the overall structure of the Hardhat. Inside contracts, I have created a 01 reentrancy directory. Inside this directory, we have the contracts related to the DAO hack. First, let us have a look at vulnerable DAO.sort. Inside vulnerable DAO, it reproduces the 2016 the DAO reentrancy bug. The external call happens before the balance is updated. So the receiver can re-enter withdraw while the ledger is stale. Let me explain in the code what this means. Here we have our withdraw function. Inside withdraw, first we fetch the balance of the caller. Then we check that the balance or the amount must be greater than 0. If it is greater than 0, then we go ahead and make the external call. This call is transferring the ETH balance of the caller, and then after the external call, we update the state, which is wrong. First, we are making the external call, then we are updating the state. This is our vulnerable DAO smart contract. Now let me open the attacker smart contract. How the attacker executed the DAO hack. Here we have our vulnerable smart contract, and here we have our attacker contract. So what exactly happened? What the attacker did, the attacker deployed this attacker smart contract on the Ethereum mainnet. Okay, and from within the constructor, the attacker got hold of the DAO contract address and set that into the DAO state variable. This is clear? Then from within the attack function, the attack function was called with exactly 1 ether. When the attack function was called with exactly 1 ether, the first check or the check at line number 21 got passed. Then let me explain the sequences. Then what happened? First step, the attacker called DAO.deposit. So what it did, it executed this function, deposit, and updated the state variable balances for the attacker smart contract, assigning the value of 1 ETH. After that, the attacker called DAO.withdraw. When the attacker called DAO.withdraw, the withdraw function was called. Here, the balances of the caller was fetched, which was retrieved from the state to be 1 ether. Hence, this check got executed successfully, and after this, the external call was made. Once the external call was made, what happened? Have a close look at message.sender. Message.sender is the caller. Here, message.sender is the attacker contract itself. In case of contract, if you are transferring ETH to the contract, so what happens? The receive function kicks in. The receive function kicks in, and inside receive, the attacker added this line which checked that the balance of the DAO contract, if it is greater than 1 ether, keep on calling DAO.withdraw. So from line number 20, the receiver function was invoked. Inside the receiver function, it checked the address, it checked the balance of the DAO contract. If it was greater than 1 ether, again it invoked DAO.withdraw. So what it did? Again it invoked DAO.withdraw. Now notice the reentrancy loop over here. From the external call, right? From the external call, again we are calling DAO.withdraw. Now you may see or say But we already have a check. But we already have a check which ensures that the amount must be greater than 0. Yes, but this check would have kicked in if the line number 24 would have been moved up before the external call. Now, since the state was updated after the external call, hence the attacker was able to re-enter and drain the DAO contract with all the funds. So this is the reentrancy attack. This happened in case of vulnerable DAO. Now what was the fix? The fix was straightforward. Let me open Save DAO. Inside Save DAO, as you can see, we have our withdraw function, right? First, we fetch the balance of the caller, then we check that the balance should be greater than 0 and we update its balance to 0. Then we make the external call. Now, in this case, what happened after the external call, even though the attacker called withdraw function again, right? After calling withdraw function, what happened? It got failed at this check because before calling or before making the external call, we have successfully zeroed the caller's balance. Hence, the next call got failed at the require statement. One line of code at the wrong place cost was equal to $60 million. But more than that, the Ethereum blockchain got split into two. The current Ethereum blockchain, which uses proof of stake, and the Ethereum Classic blockchain. So this is the importance of auditing your smart contracts. A single piece of code or a single line of code can lead to a financial loss of $60 million. That is the severity of auditing smart contracts. Since we have looked at the vulnerable DAO contract, then the fix in the saved DAO contract, and how the attack actually happened. How are we going to ensure that whatever we did is working as expected? So for that, we will switch over to unit test cases. Let me close the whiteboard. Reentrancy test.js. Let me expand this. So what we have decided, first we will run the exploit, then we will fix the bug, and on rerunning the test cases, the exploit should not work. Let me open laser pointer. Yes. So here we have a funded DAO function. Inside funded DAO, it takes a name parameter. This name is the name of our contract. In case of exploiting the bug, we will pass in the name to be vulnerable DAO, which is our vulnerable DAO contract. And in case of after fixing the bug, we will pass in the name as save DAO. Here we get our accounts from ethers.getSigners. Then we get our contract artifact from the name. After getting the contract artifact, we initiate the deployment transaction. Then we wait for the deployment of the contract. That is, we wait for the inclusion of the contract creation transaction into the block. After that, there are two users, Sakshi and Om. Both of them deposit 5 ethers into the DAO contract. And then this funded DAO function returns the DAO contract object, and the attacker account. Our first case is exploiting the bug. So what we do, the name parameter for the frontend DAO function, we pass it as vulnerable DAO. So here the DAO contract object is our vulnerable DAO smart contract, which has a reentrancy bug. This is how you get the contract address using .get address, and we store that into the variable DAO addr. Why we store that? Because our attacker contract, right? Our attacker contract takes in the DAO contract address in the constructor. After getting the DAO address, we expect or we verify that the initial balance of the DAO contract is 10 ethers. Why it is 10 ethers? Because Sakshi and Om have already deposited 5 ethers each. So line number 20 ensures that prior to the hack, the DAO has 10 ethers in it. Then we deploy the attacker contract. After deploying the attacker contract, what the attacker does, the attacker calls the attack function. Now let me explain what this .connect means. If you want to invoke certain function with a certain wallet address, then you use the contract object .connect and pass in the signer or the wallet account, right? So this attack function will be called from the attacker contract, and for this attacker contract we are passing 1 ether because inside attack contract we have this require statement. This should pass. Once we call the attack contract, ideally what should happen? The balance of the DAO vulnerable DAO smart contract should be 0. So that's what we are checking it. So at line number 29, we again fetch the balance of DAO address and store it into a variable pool after. And then we call our attacker's loot function. So attacker's loot function returns whatever the amount of ETH that was stolen from DAO is now stored into the attacker smart contract, and this loot function returns that balance. Then we verify that the exploit has executed successfully with line number 33 and 34. We expect the DAO contract balance to be less than 1 ether, and we expect the loot or the amount stolen from the DAO contract to be greater than or equal to 10 ethers, which is approximately 11 ethers. Hence, from the first test case, we have exploited the bug. However, we also said we will fix the bug and rerun the test cases to ensure the attack doesn't work. So the second test case, in this case also, we will call our funded DAO function, but here we will pass in the contract name to be saved DAO, because inside saved DAO, we are updating the state first and then making the external call. In this case also, we get the DAO contract address using .get address. Then the attacker contract is deployed. After deploying the attacker contract, notice line number 45, the attacker invokes the attack function. However, we are expecting that to be reverted. Now this will be reverted because we have updated the state or the balances to be 0. So when the second call comes, that time this amount, right? This amount is returned as 0 and it fails at this require statement. And at last, how we verify or make 100% surety that the account or the DAO contract has all the ethers. So we check the balance to be equal to 10 ethers. Hence, we have successfully first exploited the vulnerability. Second, we have fixed the vulnerability and reran the test cases and ensure that the vulnerability is fixed. In case of DAO, the fix is check if its interaction pattern, that is state, is updated before the call. Plus a reentrancy guard has defense in depth. What is a reentrancy guard? Reentrancy guard is a smart contract which you can inherit from OpenZeppelin library. This ensures that if the external caller is trying to enter or re-enter your contract, this modifier non-reentrant will not allow that second call to execute. Let us run these test cases on the terminal. First, I have to change, okay, I am into the correct directory. Then after this, let me run npm run compile, then npm run test reentrancy. Here it is. Initially, vulnerable test ran, attacker drains the entire pool, and after fixing the bug, right, the identical attack fails and the pool is untouched. This is what is expected from all the students. You are given the smart contracts related to all the hacks, right? So these are the smart contracts for access control. These are the smart contracts for signature verification. These are the smart contracts for privilege trap. And you are already given this reentrancy.test.js file. All these things are shared with you on Google Classroom. The assignment or the lab part for you is to complete the test cases for access control, signature verification, and privilege trap. This will make sure that you understand the lab end to end, and this learning will persist with you in the long run. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.